Hello physics fans, I'm Mr. Zentis, and what I'm going to talk about is Chapter 5. Chapter 5 is all about energy, and today I'm most specifically interested in elastic potential energy. I'm on page 170 of your whole text, and we had already discussed gravitational potential energy. And gravitational potential energy, we said, was mass times the acceleration due to gravity times the height. Well, another type of potential energy is elastic potential energy, and these are really the only two types that we're going to address. I'll leave the potential energy of chemical potential energy for later, and for biology. But energy stored in compressed or stretched objects is elastic potential energy, such as the energy that's stored in the strings of a tennis racket. That would be potential energy. Once those strings are stretched, then it has potential energy. And what we're going to do mostly, we talk about the energy that you find in a spring, and once it's compressed, it has stored potential energy. So there's a couple of different parameters that we need to address in order for you to understand this equation. First, what we mean by the relaxed length and the compressed length. All right, so what we mean by the relaxed length of a spring is, of course, the length without a force. That would be considered the relaxed length. Then, if you compress it, you apply a force. You apply a force, and then you have the compressed length. So this is relaxed, and this is compressed. All right, now the difference between these two is d would be displacement, and that's important to recognize what the displacement. What it is the distance from relaxed to compressed, and it requires work to do that. And remember, work equals force times distance. So we're going to try to, what we're going to try and do is talk about the relationship between this work equation, work is force times distance, because we applied a force over a displacement, and the potential energy that we have in the spring. Well, the force of the spring is equal to the force constant times the displacement, times d. And I should consistently use a lowercase there. The force is the force of the spring is going to be in the opposite direction. So technically this is negative, but I'm going to try not to confuse you with this. And this is referred to as Hooke's law. And we're going to take Hooke's law and we're going to combine it with work. All right. Now, if we plot the data of force that it takes to compress a spring over the displacement, and that's going to be in meters. If we plotted this data and we took the area underneath the triangle is work. So work is the area underneath the triangle, and so the area under the triangle is 1/2 base times height. So if we plot this data, it shouldn't take us very long. If we force is 1.3 3 and 6 7 4 and 1, 5 and 1.3, and 6 and 1.5. And we do draw a line of best fit. The slope of this line, is, so the slope of this line is the spring constant. The area underneath the triangle is work. So the spring constant is the slope of the line. Change in force over change in x. Right? So if we said change in force over change in x, and if we went we'll start at 0. That's the convenient thing. Over 1.5, and these are meters and these are newtons, by the way, minus 0. That makes it convenient because then we're just doing 6 newtons over 1.5 meters, excuse me, and that's 4 newton meters is the spring constant. As you can imagine, every spring has a constant because not all springs have the same resistance. The bigger the constant, the harder the resistance, the harder it is to compress the spring. And so you have to find out what that is before you can determine the force. Okay, so the potential energy in the spring is found in calculating the work done in compressing the spring. The compressed spring has stored elastic energy. So if we combine the area of the triangle to find the work with Hooke's law, we come up with potential energy equals 1/2 K, which is that spring constant, times X, which is the displacement. Right. So I was just trying to show you how I derived that with those, but this is the equation that we're going to use. So let's give it a go and see how it works in this sample problem. A spring with a constant of 4.0 newton meters is compressed by a force of 1.2 newtons. What is the total elastic potential energy stored in this compressed spring? Well, as you look at this problem, the first thing I notice is that I don't see my displacement, my m. But what we do know is K equals 4 newton meters, and we do know that the force of the spring equals 1.2 newtons. So we're going to use force equals 1/2 K kx squared to find the potential energy. But before we do that, we're going to need to find x. And in order to find x, I think the easiest way to do it is force of the spring equals kx, and so x equals force of the spring over k. So 1.2 newtons divided by 4 newton meters equals 0.3 meters. So now that we have our meters, we can plug the numbers into our equation. So potential energy equals 1/2 4 newton meters times 0.3 squared, and those are meters, and that equals 0.18 joules of energy. Right. Let's try one more. A spring with a spring constant of 80 newton meters is displaced 0.3 meters from the equilibrium position. Find the potential energy stored in the spring. Well, we could use our potential energy 1/2 kx squared. We know x equals 0.3 meters. we know the spring constant. The spring constant is 80 Newton meters. So we should be able to solve one potential energy is one half 80 Newton meters times 0.3 meters squared, or 3.6 joules.